Hi, my name is Ed Vielmetti. I'm a senior ecosystem engineer at Packet, an Equinix company. And my presentation today is on environmental system monitoring with Grafana, Prometheus, and Tailscale. Why did I do this talk? And the motivation for it is fairly simple. With the current situation, I'm spending a lot of time in my attic, which is the hottest room in the house during the wintertime, during the summertime, and the coldest room in the house during the wintertime. It's my worry, I guess, when I started this is that the attic was too hot for the equipment that I've had. But more generally, knowing the temperature of the room and knowing the temperature of a bunch of things in the room is a relevant question for data center operations. So the task at hand is treat the home lab, treat the attic as if it were the very worst data center that you had in your collection. It has the worst network. It has the worst environment. It's the least reliable. It's the one that's the hardest to get to if something goes wrong. And see if I can answer some simple questions. So the simple questions for me really are about being aware of the small changes that I can make to make the attic more habitable. Do I open the window? Do I get a fan? Do I get a bigger fan? Do I point a fan at one of the computers that I have so it doesn't get so hot? How big a fan do I need? All those sorts of airflow questions. And then try to get some take on some of the harder questions like, do the systems I have, are they running slower than they should be because they're too hot and they're being throttled down? Or is it so extreme that the lifespan is going to be diminished? Or in extreme cases, and I'm glad to not be in one of those, but in data centers, sometimes if a fan fails, it'll burn out the equipment and you lose some gear. So there's temperature in the data center is a relevant question for a lot of things. As it turns out, I've been able to do all this without buying a lot of extra equipment. And that was another big part of motivation is like, can I reuse what I have? The home lab here has a bunch of Raspberry Pis. It has a Jetson Nano. One of the Pis has a SparkFun Quick hat, which is a little hat that has some sensors plugged into it. I think I can show you that right here. There's the hat plugged into it and the little sensor devices. And then I've got access through Packet to equipment in data centers. A variety of ARM64 servers that are part of the Works on ARM project that I run at Packet. So there's a variety of things to test out, and that's what I did. And I didn't have to go and have a big budget for new equipment to do this. So stated simply, a goal is to be able to check the attic temperatures from my phone, but not to share any of this information with the world. And I have to say, monitoring temperatures in your house is a very old problem. The first one that I was aware of was a friend of mine in the early 1990s who had a hot tub at his house. And Paul had a thermocouple attached to his Sun workstation and was able to tell whether the lid was on and off. He had a servo motor hooked up to a little thing to wave to his cats. This was nearly 30 years ago, so this is not new. So what I thought I would do to make it new and worthwhile of a talk is reuse some cloud native tech for home automation, which is why you're seeing Prometheus and Grafana, more Prometheus here than the other. Try to do something that was relevant to the data center. So for the attic, just read Edge Data Center and try to imagine that this is how that works. Make some privacy goals using a VPN. And since I'm setting up a VPN for access so that I can check things from my phone, also set up the same VPN so that I can do access to the sensor net from that. So problem number one is building the network with WireGuard. WireGuard is a very interesting piece of technology, and I'll motivate why it's a solution for it, and then why I ended up using Tailscale as the implementation of WireGuard to do this. So VPNs let you build out a flat network rather than a segmented one when you're looking at a bunch of devices that are on heterogeneous networks. The one approach to sensor network gathering is to have a sensor network where you have a series of layers between your sensor and the final collector to the device. And if the sensor talks to an aggregation layer, and then the aggregation layer talks to a collector, you really have two sets of networks to manage. With the VPN, instead of having smart devices traverse firewalls, you make each of your sensors smart enough to traverse firewalls, so that you can make the hard work of collecting data go through the smart network. And so it's a purpose-built private network. It's sort of a dark net. It's not available to the whole internet. You can put devices on it or services on it that wouldn't otherwise be visible to that. So the first try I did of this was with a tool called WireGuard. WireGuard's built into the Linux kernel with the latest kernels, but it has very bare bones management and control plane primitives. And I was able to get some pieces of this working as my network got more complicated, the configuration got more complex to the point where I didn't quite understand what I was actually doing. WireGuard's a very good source for underlying protocol for VPN connections. There's a presentation that the author Jason Donenfeld did at FOSDEM 17 that's worth looking at. But as a user interface, it leaves a lot to be desired. And so what I switched to instead was a tool called Tailscale. Tailscale is a commercial product. It's just out of beta test, written by some folks who were formerly working on the Go language, with a management and layer and a control plane for a WireGuard VPN network, which what this means is you're using the same VPN protocols as have been accepted into the Linux kernel, but the management data plane is smarter, and in particular, it has some really clever functions. You can see all the nodes in your network and easily add to subtract from the network from a dashboard. Dashboards are, again, not new, but this is an easier configuration than it is in the native WireGuard world. Tailscale will punch holes in your network. So if you have a firewall that goes from one side to another, and normally traffic can only go in one direction, you can punch a hole, and the Tailscale protocol will allow you to have two-way communication just between those two machines, just traversing this information. For really difficult situations where you have multiple firewalls or multiple systems, both behind firewalls that need to have unfettered communication with each other, they have a clever protocol of theirs called Designated Encrypted Relay for Packets, otherwise known as DERP, and it'll handle unusual or mobile or multi-hop firewall traversal situations. Pricing is free for single user use, which is why I'm doing this. Again, the goal was not to buy a bunch of additional stuff. It'll handle up to 100 nodes. The commercial product has a tiered pricing based on primarily on enterprise features. And just to be clear, this is a product that I'm using. This is not my product. So setup for Tailscale. The setup process, I won't go through it here, but it's enough to note that it runs on Linux, Android, Mac OS, iOS, and Windows. It comes out of the box with 64-bit ARM support on all platforms except for Windows 10 on ARM, because Windows 10 on ARM is missing a Go compiler on that platform. and you use your Gmail login to log into the personal account if you have that tier of access. If you're using Tailscale, you also get access to a network on Net 100, which is a reserved net for private VPNs. Every system in your Tailscale network can see each other, but no one else can see those systems. And that actually becomes a perfect configuration for sensors. I do not want my sensor data published to the internet, but I do want to be able to access it from anywhere that's a cooperating node on the internet. And because Tailscale gives you a big, flat, private network as your control plane, it's very easy to take two devices that are in two arbitrary places and set them up so that one can see the other, but the world can't see either of them. So at home, in my home lab, I have a network level firewall that my ISP conveniently provides. That goes away for the purpose of this traffic. Importantly, for the simplicity of the network, the sensor and the collector can talk to each other directly. That's because my sensors are uniformly connected to Linux networks, Linux hosts, rather than controllers, which was suitable for my needs. If your node is mobile, if you're connected through your phone, it'll either connect on your local network or remotely, depending on where you are, and you don't have to separately configure that, so you don't have to work too hard for that. And finally, again, for the purpose of not making things more complicated than they need to be, you don't need to have a multi-tier message passing network. You can simply query the sensors directly from the controller, the control node, and not have a separate message handling system in between. Okay, so that's Tailscale. We have a big flat network. We're going to collect some data. We're going to collect it in bulk rather than one message at a time. And we're going to use a tool called Prometheus for that. Prometheus comes from the cloud native world. It's designed for cloud native scale data collection. So if you were running a large Kubernetes cluster with control plane and dozens of worker nodes, it would be handy for that. And I knew that the tiny scale network that I was building would not tax its capacity, even running on systems as small as a Raspberry Pi 3. Prometheus is available for ARM64 as of the 1.0.0 release. I think there was a bug that came in that you really wanted to run 1.0.2, but in any case, it was available. It easily lets you gather and store and report on literally thousands of metrics. And it plays well in an ecosystem where other tools can easily feed into Prometheus, and Prometheus can feed into visualization tools. And so the goal there is to identify places where you can use Prometheus directly to scoop data off of sensors in bulk rather than all at a time. So I was saying we have many sources of sensor data for the that can be used in this sort of system. And I want to go through these in a little bit of detail because they illustrate some of the less, some of the more interesting bits of how thermal data came into the system and how some parts of it were much easier to do than others. So taking it from the middle, Prometheus has a set of tooling called a node exporter. Now, what a node exporter does is generally collect as much data from a Linux system as it possibly can. This is hundreds or potentially thousands of values, system load averages, disk usage, process counts, various data for various processes on the system. And then also it'll look at hardware functions to the extent that it can find them. Much to my surprise and my delight, on the systems that I was using, it could read the thermal sensors that are built into the CPU. Now, you might ask, why is there a thermometer in my computer? Which is a real good question. And it turns out on some computers there are dozens of thermometers. They get used primarily as part of thermal controls so that the computer can instruct either the computer directly can instruct a fan or some other active cooling device to turn on and off. Or in the case where the thermometers are built into auxiliary baseband management controllers, the BMC itself can turn on fans through an IPMI, through a I2C interface, and control fan speed. And as it turns out, the node exporter will collect everything it possibly can, which is great. Most of the time, people don't even notice that there's one or a multitude of thermometers hiding out in their system. The second source of data that I took a look at was specialized sensors that were actually peripheral to the device. I showed you at the start this SparkFun quick p-hat. It has a sensor built on top of I2C or I2C, and so as a device, it reads a single value from a single chip. Now, it turns out that this exact device was part of a talk at a previous ARM TechCon, and when that project ended, I was able to repurpose it. So it's the same device. To get it to read from the sensor, all I had to do was adapt some sample code from the SparkFun folks to spit out data in the format that Prometheus wanted. And finally, for IPMI, what I did was use a package from the folks at Soundcloud that's an IPMI exporter. If you're not familiar with IPMI, you may not completely realize that on board a typical server device is a chip called a BMC, or a baseband management controller, which is a full-blown computer in its own right that controls the basic operations of the server that you're running. So the BMC can turn the computer on and off. It will spin up fans because it typically has fan controls. And it has IPMI, which is a protocol to provide access to all this information. So again, I'm using the IPMI tooling from SoundCloud to scoop up the thermal sensors that are usually used to control fans and to just collect the data from them. And with this is essentially the full range of data that you might expect: the built-in data, a specialized sensor, or specialized sensors that are built into servers. To scoop the data off the quick p-hat, there's a tool called a text collector. This actually took a fair bit of time to find, so I'm happy to share it with you. Essentially, you're gathering additional custom metrics from a host with a very simple standard interface for custom stats gathering. And what that means in practice is that any language that you're capable of writing a short script in, you can read data off of anything you find, whether it's a radio protocol or a attached device or a website or what have you, and compress it into the easily readable ASCII format that the text collector expects, and export it into your infrastructure. The server data export from IPMI with the tooling from Soundcloud is an example of bigger system architecture that the Prometheus system allows. So the Soundcloud tooling looks at that on-chip data and exports it again in the same standard configuration format. And because it has not just a couple of temperature sensors, but dozens, it might have a sensor for looking at the temperature of inbound airflow, outbound airflow, fan speed, on-chip temperatures measured at a bunch of different spaces. And you can start to answer the question of how well is the data center temperature controlled, and how effective are the fans that you have at keeping the data center and your servers at an appropriate ambient working temperature. I'm going to skip over this section with Grafana. Grafana is a wonderful tool with graphs and charts and alerts. And unfortunately, I did not manage to get as good at Grafana as I needed to do this justice. So the recommendation was to just skip things over on that to lessons learned and some concluding thoughts. First of all, the most important thing I think I saw from this was how much easier it is when the network is simple. If you have a big flat namespace and any-to-any connectivity, no firewalls, no bridges, but also make this network a dark network with no connectivity to the public internet, it's very much simpler to arrange things. So I'm not dealing with access tables. I'm not dealing with firewall rules. I'm not trying to protect at the IP layer. I'm simply building out a network that has nothing in it except the machines that I want. And I think that's part of the goal of Tailscale, not to try to do this at a scale that's global, where you would have to worry about all those sorts of things, but just to build a convenient and helpful private network for your work. Lessons learned number 2, there are sensors everywhere. And for the environmental piece, mostly this was about fans and where anything that needed to control a fan would need to know the temperature was. But even a tiny little Raspberry Pi has at least a couple thermal numbers that you can read out. The Jetson Nano had, I think, 6. And then the IPMI infrastructure for some of the high core count machines would have multiple on-die readings plus other sorts of things. And this is a test of modern server firmware to make sure that the thermal zones available to monitor are accurately and carefully kept cool by the fan stuff. And if you ever brought up a server that's an early version of it, you might discover that the first version of the firmware just turns the fans on high because that's the safe setting. You're generally a lot happier once the firmware matures enough to do things. Excuse me. And then lessons learned number 3, the home lab is interesting to treat as a data center, and there's really a lot more than meets the eye there. And, they have lots of real-world constraints, budget constraints, heating and cooling being parts of it. You'll notice if you're monitoring one of these edge data center style installations compared to a full-on core data center, you'll see that the temperatures vary a lot more during the day and between days than they will in more climate-controlled considerations. Power and cooling is always a factor. I won't show you my power strip, which is full, but the fan is now turned off because it's not as hot here in the fall as it was in the summertime. But noise and cooling is a limiting factor for a lot of these sorts of things. Especially in the current world, a lot of prototyping gets done in home labs. So it's nice to think about them as a first-class situation. And it's much easier to get into a home lab than into a corporate lab in the current pandemic. So happy it was for me to have a place to experiment. And with that, thank you. Happy to share anything, questions that come up. Also happy to share pointers in additional information. Anyone who would like to know more. Apologies for not showing more about Grafana, but I just couldn't do it justice. But there's lots of data to collect and to graph neatly. And with that, thank you very much.